The idea that mass could be negative sounds completely absurd at first glance. And no, we're not talking about antimatter here, but about something even stranger: matter with negative mass. Normally, we don't describe mass as positive or negative. It's just mass. If we tried to make the analogy, it would seem simple. An object weighs 5 kilograms. To make it negative, we just slap on a minus sign and call it minus 5 kilograms. But what would that actually mean? How could something be less than nothing, especially when we're talking about real, physical stuff, not abstract things like bank balances? It sounds like pure nonsense. And yet, the concept of negative mass, or more precisely, negative mass energy, has fascinated physicists for decades. Despite sounding illogical and impossible, it isn't outright forbidden by our physical theories. In fact, it shows up in some advanced, though highly speculative, ideas. Today, we'll explore what negative mass really means, whether such exotic matter could exist, and whether there's any experimental or observational hint that it might be real. We'll imagine what negative mass would look like, how it would behave, and even what might happen if parts of our universe contained it. And finally, we'll ask, could a negative mass engine, one that runs without consuming energy, actually work? Albert Einstein introduced special conditions in his general theory of relativity, one of which states that energy cannot be negative. Since energy and mass are equivalent, this also implies that mass itself can't be negative. Einstein added this requirement to avoid strange, non-physical solutions to the equations of gravity. However, later researchers showed that simply putting a minus sign in front of mass in the equations doesn't actually break the math. The theory still works. There are no infinite values popping up or other obvious inconsistencies. In short, the idea of negative mass doesn't fundamentally contradict either Newtonian mechanics or general relativity. But just because an idea isn't forbidden by theory doesn't mean it exists in reality, and we can't fully rule it out either. So what would negative mass really mean? What would such exotic matter as physicists often call it actually be like? We know that besides mass, matter can also carry charge, and charge can be positive or negative. Could mass be similar? Even without bringing negativity into it, the concept of mass isn't straightforward. You often hear that mass is the measure of the amount of matter, basically how much stuff something contains. And before quantum theory, before the discovery of elementary particles, that was a workable idea. The universe seemed to be built out of tiny, solid particles, and mass was just how much of that you had. In that view, the idea of less than nothing doesn't make sense at all. But modern physics paints a far stranger picture. Our particles aren't tiny billiard balls. They're excitations of underlying quantum fields. Even the mechanism that gives matter its mass is highly non-trivial. You've probably heard that the Higgs field gives particles their mass. That's partly true. The Higgs mechanism does play an important role, but it's not the whole story. In fact, a large share of the mass of ordinary matter comes from the strong nuclear force, the same force that binds quarks together inside protons and neutrons and holds those protons and neutrons inside atomic nuclei. But the full story of where mass comes from is complex and deserves its own deep dive. When we ask whether mass could be negative, we first need to clarify which kind of mass we mean. In classical Newtonian mechanics, there are essentially two or more, precisely, three related concepts of mass: inertial mass and gravitational mass, with the latter divided into passive and active forms. Inertial mass is the familiar m in Newton's second law. It measures how strongly an object resists acceleration, how hard it is to push, pull, or slow down. Gravitational mass relates to gravity. Active gravitational mass describes how much gravity an object generates, how strongly it pulls on other bodies. Passive gravitational mass describes how strongly an object responds to gravity, how it accelerates when placed in a gravitational field. Newton's theory assumes that active and passive gravitational masses are equal for any object, but it doesn't require inertial mass to equal gravitational mass. That equivalence was discovered experimentally and later became central to Einstein's general relativity. So when we talk about negative mass, which one are we talking about? Depending on the situation, we will experience different effects: how bodies will react to non-gravitational forces, to gravity, and how they will interact with each other. Let's start with a simpler picture: Newtonian mechanics as described by Hermann Bondi in his landmark paper on negative mass. Imagine a bizarre object whose inertial mass is negative, but whose gravitational mass is positive. Such an object would respond to forces in the opposite way a normal object does. Push it forward, and it accelerates backward. Yet, Gravitationally, it would behave as usual. It would still be attracted to other masses and pull on them in return. Flip the situation. Suppose the object's inertial mass is positive, but its gravitational mass is negative. Then it would resist pushes and pulls in the normal way, but its gravitational interactions would reverse like magnets gone wrong. Similar masses would attract, opposite ones would repel. And if both inertial and gravitational mass were negative, then things get truly strange. The object would accelerate opposite to any applied non-gravitational force. You push it one way, it goes the other. Yet in a gravitational field, it would fall normally toward other masses. At the same time, the gravity it generates would be repulsive, pushing ordinary matter away. In short, bizarre, but still mathematically consistent within Newton's framework, which works surprisingly well in many everyday situations. But modern physics goes further. Einstein's general relativity, GR, merges inertial and gravitational mass into a single concept, the equivalence principle making them fundamentally identical. Here, we no longer separate inertial and gravitational mass. There's just mass energy shaping space-time. So if we imagine negative mass in GR, the rules simplify, but the behavior gets no less strange. Apply a force to an object with negative mass, and it still accelerates opposite the push. Picture shoving a shopping cart made of exotic negative mass. It would roll toward you. Gravity is even weirder. A negative mass object falls down just like normal matter. Let go of a negative mass ball, and it won't float away. It drops. We're not talking about anti-gravity. However, the field that this object itself creates has an effect we're not accustomed to. Look at this visualization of gravity from the perspective of general relativity, which shows how mass and energy create a kind of dent in the fabric of spacetime, and the trajectory of other objects is determined by this dent. And it's important to remember that these are just two-dimensional, simplified visualizations. In reality, such distortions look more like this. So, a body with negative mass would create a dent in the opposite direction, and a body with less mass wouldn't fall into the gravity well. Rather, it would be ejected. In short, a body with negative mass actually repels other bodies, and this leads to an interesting conclusion. Now, let's imagine we have two bodies with the same amount of mass but opposite signs. One is positive, the other negative. We place them alone in deep space, far from anything else, so nothing disturbs their motion. Put them on a straight line. The positive mass body will attract the negative one, while the negative mass body will repel the positive one. That sounds like it should break a few fundamental laws of physics, but surprisingly, it doesn't have to. It's tempting to test this with a physics simulator. Suppose we just add a minus sign to an object's mass. Would the simulation handle it? Many simple online demos don't even allow negative values. For example, take a basic spring mass setup. You can change the mass to something huge, no problem. But if you try to type -5 kilograms, the program refuses. Too bad. But more advanced tools sometimes do let you cheat. In Universe Sandbox, for instance, you can directly edit an object's physical properties. Let's experiment. Take a simple spherical cow with a mass of 550 kilograms. Type in a minus sign. Done. Negative mass accepted. Of course, with just one object, nothing interesting happens. So let's try two. We'll place two bowling ball-sized objects a meter apart and zero out their initial velocities so there's no extra orbital motion. Now, flip the mass of one ball to negative and hit run. Instantly, they shoot off in the same direction, exactly as theory predicts. The positive mass attracts the negative one, while the negative mass repels the positive. Their speeds increase as they go. You can literally watch the velocity climb. Honestly, I didn't expect Universe Sandbox to handle negative mass this cleanly. It's fun enough that you can start testing other setups, like editing the solar system model. What would happen if the moon suddenly turned negative? With its normal positive mass, the moon orbits the Earth as usual. But now, imagine we simply add a minus sign to its mass. Surprisingly, not much changes at first. The Earth's mass is vastly greater, so its gravitational pull still dominates, and the moon's repulsion is almost negligible. But what if we flip the sign of something much bigger, say, the sun? Now that's a very different story. The sun's enormous mass would turn from attractive to repulsive, flinging planets out of the solar system in every direction. Our entire cosmic neighborhood would become violently unstable. So far, we've talked about how negative mass matter would behave, but we've also made a couple of huge assumptions. Chief among them, that such matter could actually exist in the first place and not just as an isolated particle or a mathematical curiosity. Could a macroscopic object, something the size of the moon, or even a rock, be made of negative mass? Robert Forward, in a classic paper we'll return to later, pointed out, because negative matter responds to a force by moving in the direction opposite the force vector. Ordinary molecular cohesive forces cannot hold a collection of negative matter particles together unless they obey a special law of interaction. In other words, a clump of negative matter might simply fly apart its own forces, unable to hold it together. And even deeper, some theorists argue negative matter couldn't be built from familiar building blocks at all. One article notes, ordinary matter is solid because the Pauli exclusion principle keeps electrons from overlapping in the same energy state. We don't know what negative matter is, but we know what it isn't. It wouldn't be made of electrons, protons, and neutrons. Without the Pauli exclusion principle, such matter would be impossible to hold together. So, while the equations don't forbid negative mass, the very structure of matter as we know it may prevent anything large and stable from forming out of it. So, in the end, we probably couldn't hold a chunk of such exotic matter in our hands. It would simply slip right through, unable to stay solid. But again, it's worth stressing. We don't actually know what this kind of substance would be like if it exists at all. So we can't fully rule out the possibility that it might be used or harnessed in some way. No one has ever seen a macroscopic piece of negative mass matter. Yet, as we've said, the very idea of negative mass and negative energy isn't forbidden by modern physics. In fact, these concepts sometimes appear deliberately in theoretical frameworks, especially in quantum physics. Even more intriguing, there are real physical effects where something like negative energy seems to appear. Strictly speaking, negative mass and negative energy aren't identical terms, but in many contexts, they're closely related and often used interchangeably. One famous example is the Casimir effect. You'll often hear it cited as evidence that, in certain regions, energy can become negative relative to other regions. That may sound confusing. If one area just has less energy than another, how does that make it negative? The key is that here, we're not comparing ordinary energy levels, but the vacuum itself, the lowest possible energy state of the universe. Or at least, what we think is the lowest. Whether it's truly the ultimate ground state is another deep and open question. Let's remind ourselves how the Casimir effect works. Even if we could strip a region of space of all matter, particles, and energy, creating what we'd call a perfect vacuum, quantum field theory says the underlying fields themselves don't vanish. They remain, just sitting at their lowest possible energy state. And on the quantum scale, empty space isn't really empty at all. It seethes with fluctuations, a restless sea where pairs of virtual particles constantly pop in and out of existence. In the case of the electromagnetic field, those would be virtual photons, particles of light that briefly appear and disappear. Now to the effect itself. Imagine two uncharged, perfectly reflective plates placed very close together in a vacuum. Virtual photons of many different wavelengths exist everywhere, but long wavelength modes can't fit between the plates. The gap is too small. Outside the plates, though, all wavelengths are allowed. The result is a tiny but measurable pressure difference. There's slightly more radiation pressure outside than inside, and the plates get pushed together. This phenomenon has been confirmed experimentally many times, and it strongly supports the idea that quantum fluctuations are real. But here's the interesting part. The region between the plates can be described as having negative energy relative to the surrounding vacuum. How does that work? Well, if you take a chunk of perfect vacuum, its energy is defined as 0 on average. But 0 here is a balancing act. Those virtual particles are constantly winking in and out, borrowing energy for an instant. When the plates exclude certain fluctuations, the average energy density between them drops below that of empty space outside, effectively going negative compared to the usual vacuum level. This negative energy interpretation of the Casimir effect isn't universally accepted as the only way to describe what's happening, but it's a common and useful picture. And it's not the only place negative energy appears in theoretical physics. Cosmology provides even more dramatic hints. Inflationary models of the early universe often involve regions with effectively negative pressure or energy density. And today, we know the universe isn't just expanding, it's accelerating. Something must be driving that repulsion, and we call it dark energy, though we have no idea what it actually is. Its effects are the opposite of gravity. Some hypotheses, like the dark fluid model, even propose that what we think of as dark matter and dark energy could both arise from a single underlying substance with negative mass-like behavior. Here's where things get really speculative. Some researchers have proposed that a kind of dark fluid with negative mass might actually exist in the universe. In theory, such a fluid could explain two of the biggest cosmic mysteries at once: the accelerating expansion of the universe, usually blamed on dark energy, and the strange motions of stars in galaxies and galaxy clusters, usually blamed on dark matter. But making this idea work takes some serious assumptions. For one thing, if this negative mass fluid were driving cosmic acceleration, its density in any given region should drop as the universe expands, meaning its influence should fade over time. Yet, observations don't show that happening. The author of the idea suggests a workaround. The dark fluid might be continuously created, somehow appearing out of nowhere as the universe grows. That's reminiscent of the old steady-state theory, which once tried to explain cosmic expansion by proposing that new matter was constantly forming. The difference, the author argues, is that here we'd be creating negative mass rather than ordinary matter. Still, it's a bold leap. And you may remember headlines a few years back claiming scientists had created negative mass in the lab. Classic case of media hype. In reality, no one conjured exotic negative mass matter. Instead, physicists engineered conditions where a normal substance, in this case, rubidium atoms with perfectly ordinary positive mass, behaved as if it had negative mass. They cooled the atoms to nearly absolute zero, forming a Bose-Einstein condensate, and then manipulated them so that when pushed, the condensate moved opposite to the applied force, the hallmark of negative inertial mass. A fascinating trick, but not actual negative matter. Antimatter is often confused with exotic negative matter, but the two aren't the same. As far as we know, antimatter still has positive mass. For a long time, physicists could only measure its inertial mass directly. They assumed its gravitational mass would also be positive, but wanted to check. And just recently, they did. Experiments finally measured how antimatter responds to gravity, and to everyone's relief, and maybe slight disappointment, it falls just like ordinary matter. No anti-gravity surprises there. Still, the idea of negative mass and negative energy does have a place in modern physics. It appears in advanced theories, and we've seen real effects that echo how negative mass might behave. Yet we don't know whether it truly exists in nature. But let's set aside those details for a moment, whether negative mass is real, whether we can produce it in useful amounts, and so on. Suppose we could make it. What would we do with it? There are at least 3 spectacular ideas, all connected to space travel. I've already mentioned one spectacular potential use for negative mass, the warp-driven engine that would literally bend space. The idea is to create a bubble of distorted space-time around a ship. Inside that bubble, the spacecraft itself wouldn't move forward in the usual sense. Instead, space would expand behind it and contract in front of it, carrying the bubble and everything inside along. Because space-time itself isn't bound by the speed of light, this could, at least in theory, allow travel faster than light without technically breaking relativity. The concept has been a staple of science fiction for decades, but it entered serious scientific discussion after physicist Miguel Alcubierre published a paper outlining the first mathematical model of a warp drive within general relativity. In Alcubierre's model, creating the warp bubble requires a region of negative mass energy, something that would push space outward, while the normal positive mass pulls it inward. You've probably seen the famous diagrams, a dent in space-time, where normal mass curves space downward, and a negative dent on the opposite side, a hill, instead of a well representing the repulsive effect of negative mass. The early calculations, however, were discouraging. To form a warp bubble large enough to carry even a modest ship, you'd need a staggering amount of negative mass, more than the total mass of the observable universe. Later, refinements improved this picture dramatically, reducing the theoretical energy requirements by many orders of magnitude, and some models even suggest ways to avoid exotic matter altogether. But negative mass remains the original and most straightforward ingredient. The second big idea is wormholes, hypothetical tunnels that could connect 2 distant regions of the universe, or even 2 separate universes entirely. The challenge is that we don't know if a traversable wormhole, one stable enough for a spacecraft to pass through, can actually exist. Most solutions collapse almost instantly once something tries to enter. But one proposal is that negative mass could be used to hold a wormhole open and keep it stable long enough for travel. And then, there's another fascinating possibility, one we've already hinted at when talking about the strange behavior of positive and negative mass together. Remember the thought experiment with 2 objects of equal mass but opposite signs? A positive mass object attracts everything. including negative mass. A negative mass object, on the other hand, repels everything, including positive mass. So if you place a positive and a negative mass side by side, the positive pulls on the negative, while the negative pushes on the positive, and the result is that both accelerate in the same direction. It's a bizarre runaway effect. The pair essentially self-propels, with no external energy input. So why not just build a spaceship around this idea? This concept was explored, for example, by physicist Robert Forward. To accelerate a spacecraft using negative mass, you'd simply take your ship and place a chunk of negative mass matter behind it, with the negative mass equal in size, but opposite in sign, to the ship's positive mass. Then something strange happens. The ship begins to accelerate forward, while the negative mass behind it accelerates backward. The positive mass pulls on the negative, and the negative repels the positive, and together they shoot off in the same direction. In theory, the craft could keep accelerating indefinitely, at least until relativistic effects slow things down near the speed of light. At first glance, this seems like magic. We start with two objects at rest, no engines, no fuel, and suddenly they're moving faster and faster. It looks like we're creating motion out of nothing, apparently violating the conservation of energy and momentum. It feels uncomfortably close to a perpetual motion machine. Because of that, some people argue, if negative mass leads to this runaway, free acceleration, maybe it simply can't exist. Nature forbids it. However, Robert Forward argued that this runaway acceleration doesn't actually break any physical laws. Here's the reasoning. If we start with two masses, one positive, one negative, sitting at rest, the system's total momentum is zero. After they begin accelerating, the positive mass has positive momentum, but the negative mass has negative momentum. Add them together and the total is still zero. Energy works the same way. A negative mass object carries negative energy. So when you add the positive energy of the ship and the negative energy of its companion, the total stays zero, both before and after acceleration. Nothing is being created from nothing. Conservation laws remain intact. There's a catch, though. The positive and negative masses must be perfectly equal, making the total mass of the system exactly zero. That's a very delicate balance. A single dust grain or even a stray photon hitting the ship could upset it. And while the pair would accelerate in a straight line, steering or changing direction would be tricky. Still, if we ever understood what negative mass truly is and somehow learned how to produce it in meaningful amounts, we'd likely find ways to solve those engineering headaches. For now, though, it's just an elegant idea. Neither Newtonian mechanics nor general relativity strictly forbid negative mass. It could turn out to be possible, or one day a deeper theory may finally rule it out. Either way, it's a fascinating glimpse of how strange the universe might be. Thanks for watching. See you next time.